panel. Open source is always a topic that I like to talk about because it's very key to cloud and to everything that's happening in the industry today. So thank you to our panelists and our moderator, Larry Carvalho. Next up, we have SoftLayer, and Marc Jones will be our keynote speaker for the next 40 minutes. Please join me in welcoming Marc to the stage.
Thank you. Oops. Thank you. Good afternoon, everyone. I'm going to talk for the next half hour, 30, 40 minutes, about architecting and optimizing your cloud for performance. And when I say your cloud, really it's about how you consume the cloud, how you leverage the cloud for your applications, for your services, and ultimately how to derive performance from the cloud. So real quick, I work for SoftLayer. I head up product innovation. And SoftLayer is a leading global infrastructure as a service provider. We are global. We were acquired about a year ago by IBM. And we have become the cloud platform for IBM. Infrastructure as a service, direct, and then also as the cloud platform to build upon for applications and services. So I always try to come up with a slide that illustrates what product innovation means. And it's really hard for me to capture that. So I always settle on this, which is I joke that this is how I feel most days at work. I have a very fun job. I have an exciting team. And we basically look to figure out how we build the next generation of cloud by leveraging the cloud. And so we get to play with all the coolest new toys, figure out what's coming next, how to utilize it within the SoftLayer platform, and then look to the broader ecosystem as well for partners and how to best leverage our platform. So most days we have a lot of fun trying to figure out what's coming next. So before we dive into performance, I want to talk a little bit about an evolution of cloud. Definitely not going to look to define cloud. I think one of the things that I love to see, this is about, I think, my 4th year coming to Cloud Expo East and West. And to see that really cloud has come into its own now. And it's very well defined. It continues to evolve, but kind of the core of what cloud is, I think everybody understands now. And so we've really embraced this, and we look at it as an operational model. It's not a marketing term. It's not a specific technology, but really a different way to consume compute. Is really how it started. And that's evolved now beyond just compute to all the services. But it's still at the core of it has the key tenets of cloud: capacity on demand, rapid provisioning, accessible APIs. And that's really formed the foundation for all of cloud. So we look at applications that are moving to the cloud, whether it's born on the web, meaning they were really architected and built for that, or coming from the enterprise. There's really a distinction that can be made between this notion of enterprise applications versus internet scale applications. And this is something that we've seen quite a bit with our customers and with prospective customers, and particularly now the enterprise when they come in. When you talk about an enterprise application, and you're specifically looking at it, say, from a performance standpoint, the enterprise has a fairly well-defined user base. You know who your users are. You tend to know when they're going to use your applications and services. So it becomes relatively predictive. You can really kind of forecast out, understand either employee growth, usage growth, but it's still fairly well constrained. So you can plan for that easily. It's easy to scale up within your own data centers. It's easy to scale out ahead of demand. And then a lot of times, enterprise IT is looked at more as a cost center as opposed to a revenue generator. And so it tends to run very lean, very efficient, and is really viewed as something that is needed to effectively get the job done for the enterprise. And then when you look at the internet scale applications, these are the ones that tend to be born on the web. They live on the web. And they are vital to the success of that business or to that segment of an enterprise. And at that point, the globe, the worldwide users become your user base. It can become very unpredictable. You don't know when they're coming. You don't know how many are coming. So when you start talking about planning for capacity, for performance, it's more of an unknown. And so this is really where cloud starts to lend itself well to those architectures, to those designs and implementations. And for these companies, that presence on the web tends to be a revenue generator or is vital to the success of that company, which ultimately focuses on revenue. So whether it's e-commerce, support systems, or even content that helps drive customers to that site, it's vital to the success. So uptime, scalability, performance is key for internet scale applications. So we look at cloud deployments, and this is not meant to illustrate a timeline, but really to talk about, somewhat of an evolution of how cloud's been utilized and where it's going, and illustrate some of the strengths of cloud. So it really started off with, let me throw my website up. That's the Apache icon up there. I want to run my website on the cloud. And you cared about performance, but you weren't as concerned about DR, you weren't as concerned about HA. You really had maybe one node, maybe a couple nodes. And then you move to the LAMP stack, right? So then you go multi-tier. You've got your web tier, you may have an app tier, you definitely have a database tier. So then you've broken out this architecture where you have multiple nodes. And then performance between each of those nodes starts to become a concern or a consideration as you put this together. Then you move on to something like Hadoop. And Hadoop really is the kind of a poster child for scale-out architecture. So as you need to store or analyze more data, you scale it out. You scale it out linearly. But Hadoop tends to live, or needs to really live, within a data center. Performance, latency across the network as it relates to Hadoop really doesn't have to, but it really performs more optimally when it's within a data center. So you've really leveraged scale-out architecture for cloud within a data center, within a region. And then something like Cloudant, which is a distributed database as a service, was acquired this year by IBM. And Cloudant, very similar, multi-node architectures, scale-out architectures, document-oriented database. But Cloudant extends that model beyond just a single data center to multiple data centers. And at that point, the network connectivity between data centers becomes a factor. So you've extended now to multiple data centers to build out or consume a cloud solution. So performance of the network becomes a key consideration with that service. And then something like Mashery, there's other companies that do this so well, but really this notion of API as a service, or APIs as a foundation to composable systems, or the new kind of this API economy, where services are really focused around APIs to offer a variety of different logic, different services. Those tend to be distributed as well. You have to take into account everything. They tend to be backed by a database. The database needs to be performant and fault tolerant. The app tier needs to be performant and fault tolerant. And so there's kind of been this evolution of how not only cloud is consumed, but really how applications are architected, developed, designed, and ultimately implemented. And then now today we're really focused around the concept of Internet of Things, which is to say that we're rapidly getting to the point where pretty much any device anywhere can generate data, can be used to deliver a service to end users and to customers. And that covers everything from big data of sensors or small devices anywhere that are gathering volumes of data. That data has to be stored somewhere. It has to be analyzed somewhere. Social media, I mentioned sensor data, but mobile, another key one. So all this data is coming in. It could be log data. It could be actual captured data. But it has to be stored. It has to be analyzed. And it needs to be done in a performant manner. Otherwise, the devices, the sensors, they don't perform as well. And ultimately, that hits end user experience. So performance becomes key in terms of being able to serve the really market that's taken off with IoT, or Internet of Things. So we'll talk about performance, and let's talk a little bit about what performance means. So this is a pretty simple infographic from a Fast Company article, but I think it really illustrates the point to say that performance takes on many different faces. And this particular one is illustrating abandonment rate against page load time, which is probably the easiest thing to look at, to measure, and to understand. All right, the longer a page takes to load, the less likely I am to stay on that site and wait for it to load. And if it's indicative of the performance of all the other pages on that site, I may quickly abandon that site. In the same article, they talk about one of Amazon's metrics, which is to say that a 1 second page load time decrease can translate to upwards of $1.6 billion of lost revenue a year. Or Google, in the same article, they talk about 0.4 of a second decrease in search results can translate to 8 million fewer search requests a day, which directly translates into fewer ad displays, which ultimately drives revenue. So performance matters. And the notion of moving content, moving app services to the cloud in and of itself doesn't necessarily solve the performance problem. It can aid greatly in that, but ultimately it will come down to understanding a lot about what you're doing about your applications and services and how to best utilize the cloud. So from a performance standpoint, at SoftLayer, we've taken really an in-depth look at performance. And we did it a lot with some big data solutions that we've benchmarked and that we've offered, that we've leveraged internally. So we tried to understand the notion of performance as it related to big data. So these are two of the graphs that we generated. And it really was eye-opening for us. We talk about performance, we tend to think about fast. All right, so I want to make sure my app's performant, which means that I'm going to get a fast response back. And it may stop there. But when we dive into it and we look at it, there's this notion of peak performance versus consistent performance. So the graph on the top illustrates higher peak performance than the graph on the bottom, meaning that at some point in time in one of those requests, it was faster than the fastest one below it. But as you can see from the top one, it's all over the place, right? So me as a user, I may be lucky and I may hit one of the peak performance numbers, and I may think, man, that was an awesome experience. But if I'm unlucky and I'm one of the ones at the bottom, I'm thinking, man, that was a really slow, bad performance. And so contrasting that to the bottom one, which is really focused on consistent performance, very tight line. There are some outliers, but for the most part, it's a very tight line where the largest percentage of users are going to achieve a similar performance, and that performance is very strong. And so understanding that there's going to be differences in the delivery of your applications and services between what you can do the fastest and what you can do the most consistent, and trying to really marry those two together so that you're trying to achieve that peak performance, but in a very consistent manner. So there's a lot of factors that can go into this. In this case, this was a measurement of a distributed NoSQL database on a public virtualized platform on top, and the bottom is that same deployment on bare metal servers. And so there's a stark contrast between the performance of those two. So performance considerations. Compute models. So I just touched on that a little bit, but we really look at the compute models as the virtual server instances, your traditional virtualized public cloud, bare metal servers, and then private clouds. And these private clouds could be in a hosting provider where you effectively building your own cloud on top of a public cloud provider. But the virtual server instances, as I mentioned, tend to be, this is public cloud. This is where it's a multi-tenant platform. You have a slice of that server, and you're going to get performance that's pretty much relative to what you've purchased in terms of core count, memory, disk I/O. But you're sharing that underlying platform with other people. And so there's always going to be competition for the core resources. And so you're going to see a degree of fluctuation in the performance of that platform. And one of the reasons that scale-out architectures work is it allows you to get additional compute, additional network resources, additional storage resources that you can use to distribute that load across those and try to average that out. Bare metal servers, they are really focused on delivering that raw iron, where you're going to put your operating system of choice onto that. You may or may not want to leverage a hypervisor, but you can put your OS on there. It's effectively like having a server in your own data center that you install Ubuntu or Debian or CentOS onto, or RHEL. You're going to get every ounce of performance that bare metal server has to offer. And so you're going to be able to achieve more performance with that platform. And then the private cloud, if you still want to take advantage of virtualization, if you want to take advantage of kind of the key tenets of cloud, rapid provisioning, you can build your own private cloud. Now, you can do that on top of a virtualized platform, but then it's a double taxation for hypervisor tax of really limiting some of the performance that's available to you with the underlying hardware. You do have the capabilities to build out your own private cloud. You can leverage OpenStack, you can leverage VMware, and you can put it onto a bare metal server. And at that point, you're able to fine-tune that, build it out to your needs, and take advantage of that. So these are three of the kind of the core compute models that are in play today with cloud. Storage. Storage has gone from, I wouldn't call it an afterthought, but not one of the first things that you think about, to being one of the largest enablers of performance on the cloud platform. Storage varies. So from a bare metal standpoint, you have the option of local storage. With local storage, you can select, I'm not worried about performance, spinning disk, say it is okay. Or I need to have decent performance. I can go SAS, which is still spinning disk. Or I need blazing performance. I'm going to go all SSD, may introduce some flash. And I can build that all and spec that within my bare metal server. So I know that I have optimal performance within that server. From a network standpoint or from SAN standpoint, you have the ability to leverage storage attached network. With that, you get a higher degree of fault tolerance and redundancy by the nature of SAN, and it's going to go across the network. So part of the performance with storage that's network attached storage is going to be related directly to the network. So the network of your virtual server instance and the network that the storage is attached to. So just really understanding what your options are around storage and how you can piece it together to best meet the needs of the application that you're trying to run on that compute can definitely add to overall performance of your architecture. And then the network. I think network is one of the things that really now is coming to the surface of being one of the strongest and most key components of a cloud architecture. It is what everything rides on top of. So within a data center, right, all your server-to-server communication is going across your network. When you start crossing data centers, you start going internationally, the network matters. So understanding your throughput requirements, how much data do you expect to push across the network, knowing what your port speeds need to be on your virtual server instance or your bare metal server. Is 100 meg okay? Do I need to have 1 gig? Do I need 10 gig? Knowing that ahead of time will help eliminate bottlenecks that may happen down the road. And then latency. How sensitive are your applications to latency? We've seen some distributed databases that are incredibly sensitive to latency. So they need to be within the same data center. We've seen some that doesn't fit the cloud model very well because they need to have rack affinity. They need to be like within the same top of rack switch. And so understanding the services that you're using, whether it's your database, an application tier, communications between services, but understanding are there any latency issues there to help you better architect what that network looks like. And then performance. So I mentioned port speed, but building out these architectures, you're able to specify a lot of times what that port speed is going to be. So it could be, in this case, this is kind of illustrating 20 gig to the rack. So it's a very high throughput. It could be used for big data analysis. And then understanding your network. Do you have segregated networks? Is there a public network only for internet traffic? Do you have a private network that you're able to leverage to pass traffic between your servers within a data center or across data centers? And what does that network look like? Do speed tests. Understand load testing on your applications. What are the potential breakpoints as it relates to the data transfer between? And then network reach. So we're now starting to see where we've moved from a data center to a region to national footprint to now international footprint. So network reach has a number of implications. Where are your customers located? Are they all in the United States? If they're all in the United States, then it makes sense to build out your cloud infrastructure, maybe on the East Coast, West Coast, maybe in Central. If they're globally distributed, then you need to look at, do I need to architect my application to be truly distributed? Do I need to have services running in Asia, in Europe, in Australia, as well as the United States? And obviously, when you go that path, it brings up additional challenges from a design and architecture standpoint. But the beauty of cloud is it's really starting to enable these architectures that allow you to go fully distributed and push out this content closer to your end users, because it's really all about end user experience. And so when it performs well, happy customers, getting to that point really requires some upfront thinking. This is actually the SoftLayer network map. It is the network map of our existing data centers and our upcoming data centers. And so SoftLayer today, we have 15 data centers. We actually just announced today we've opened our first federal data center in Dallas. And 2 weeks ago, we opened up our Hong Kong data center. So we announced earlier this year that we're doing a $1.2 billion investment to expand globally to add 15 new data centers around the world. And that increases our data center options when you start talking about putting content closer to end users. And it also really opens up our private network, which interconnects every data center. And so you have tremendous reach to your end users with a footprint like this. And then just yesterday, we announced a new product called Direct Link. And it ties in well when you start talking about performance. The panel before me, they talked about the notion of hybrid cloud. And when we talk about hybrid cloud from on-prem enterprise or from an enterprise data center to the cloud, being able to leverage resources in both. When you do that, you typically are going to go across the public internet. And maybe via a VPN, but you're still going to go across the public internet. And it can be slow. You need to get data to and from the cloud. And so Direct Link allows customers to get a direct network connection to the SoftLayer network, 1 gig or 10 gig. So if you're pushing a lot of data to and from a service like this, it makes a lot of sense. It really enables a lot more flexibility with hybrid to allow you to maintain some or all of your core applications and services within your own data centers or on-prem, but to be able to take advantage of the cloud, whether it's burst or compute augmentation, storage, backup, DR, that type of service, and having a secure, performant, consistent network connection to the cloud greatly increases the overall performance of the platform. And then scale. Kind of taking all of those into account, scale is the ultimate with cloud. And this is really compute on demand, services on demand, allowing you to take that burst ability and apply it to your applications and services. Right? This goes back to when I was talking about internet scale. You don't know when they're coming, you don't know how many are coming, and you don't know how they're going to use or abuse your applications and services. The ability to scale when your applications are architected properly lends itself not only to just remaining up, but to having optimal performance in the cloud. So bare metal. I want to touch on bare metal for a second, as this is near and dear to our heart. As I mentioned, I've been here for 3 or 4 years and been really talking a lot about the advantages of bare metal. When we talk about public cloud, most people equate public cloud with virtualization, and that you have to have virtualization to be cloud. And we've really focused on building a platform that takes really both types of computes and put them onto an equal playing field. So we offer virtualized public cloud or virtual server instances, but we also offer bare metal servers. And it's compute on demand. It's API accessible. It's managed through the same control plane that our virtual server instances are managed through. But it gives a high degree of customization and options when you build out your infrastructure. So I mentioned the storage options that are available to you. Pick your CPU, pick your amount of memory, and really fine-tune this to meet the needs. This tends to be for demanding workloads, I/O-constrained workloads, whether it's network or disk, big data, databases, GPU-enabled servers that are doing substantial number crunching, all tend to fit very well in bare metal, and you get more performance per node than you can in a virtualized environment. And a lot of customers leverage it together. So putting your web and your app tier on virtualized that you can scale, but putting your base workload for big data onto bare metal ultimately gives better performance. And I want to touch on a couple of other projects. So we've been talking a lot about bare metal, and for the longest time it was only SoftLayer talking about bare metal. Again, everybody was talking about virtualized public cloud. But we're now seeing a focus beyond SoftLayer talking about bare metal. OpenStack has a project associated with it that they call Ironic. And it is all about bare metal provisioning, leveraging OpenStack. So OpenStack started by offering virtualization and being able to, as an orchestration and management platform for virtualized cloud. And they've extended that, right? They've offered support for containers, and now the Ironic project is building out bare metal. So building out your own cloud, if you will, that leverages bare metal is a possibility now with OpenStack. And Ubuntu, they call it Metal as a Service, but leveraging their Juju orchestration tool, they allow you to take advantage of bare metal and provisioning it like you would a virtualized resource. And just last month at the OpenStack conference, Ubuntu announced that in conjunction with IBM, that IBM's adding a lot of support to Juju to support IBM products from an orchestration and provisioning standpoint. And Ubuntu runs on the Power 8 architecture now and is able to take advantage of Metal as a Service to deploy Ubuntu onto the bare metal. So we're definitely seeing a lot more uses for bare metal as part of a cloud architecture. So design considerations. Core focus and need varies across industry, but there's a lot of commonality between them. And so this is just 4 segments that we see a lot of traction in right now in the cloud, really early adopters, not only leveraging cloud, but driving innovation in the cloud. And first and foremost, they're all about delivering their services via the cloud. But when you look at some of the underlying uses of cloud for these specific industries, API Web, they care about metrics. So once their service is up and running, they really care about metrics. Is my service being used? How performant is my service? How many error codes am I returning back? And so building out an architecture that supports not only serving the content, but being able to analyze the data, capture the data, is important for them. Gaming, adaptive algorithms. So a lot of the games these days are moving to a free-to-play model with in-app purchases. So it helps them to understand your habits. How often do you use it? When do you use it? And to adapt their algorithms in terms of offering specials or in-app purchases to try to get you more engaged and to try to open up your pocketbook a little bit more. But they need data to do that. And they need cloud architectures to capture that much data. Financial is all about machine learning, trying to understand and model the market. And then science, research. It's a lot of data capture, a lot of data analysis. So each of those industries, they really focus on some of these key design considerations. So why is scalability so hard? I've touched on it throughout, but it's because it cannot be an afterthought. You really have to think about scale when you start moving applications to the cloud. How to best take advantage of the wide variety now of core services that are available to you, as well as the additional services, whether it's PaaS or SaaS, that you can leverage for that. And it is possible, but just know that throwing more CPUs at it doesn't necessarily achieve better performance. Applications need to be tuned. Languages need to be used that can take advantage of multi-core. Stateless and async, 2 of the biggest killers of performance, I think, in designs. Stateless being that you don't have to maintain state in the cloud about user interactions. So when you have to maintain state, say you're launching a game server and there's going to be 10 people connected to it. That game server has to maintain state and know about each of the 10 players, what they're doing. And when you maintain state, if you want to have true fault tolerance and high performance, you need to be able to distribute that across multiple nodes. But that means that you then have to keep all of that in sync across all of those nodes. And that introduces more complexity, more latency, and it tends to bring performance down, and it decreases how quickly and how you can scale. So where you can go stateless, which means that my interactions don't have to maintain state. I can pass in an identifier about this transaction and have it recreated on the server side. Or I'm leveraging caching servers on the server side to help augment that. And then asynchronous. Asynchronous simply means that when a request comes in, the person that made the request is not expecting a response right away. So it allows non-blocking I/O to occur. I can pass off that request, get it processed, and then report back when it's complete. So you don't have a lot of people blocking, waiting for an answer. And then testing. This says testing async code can be non-trivial, which it can, but the key here is really testing. Test early, test often, continuously test. The advantages are enormous, not only just from a performance standpoint, but from a code coverage and you're really decreasing, finding bugs early and enhancing the overall security and performance of your platform. Eliminate choke points. We talked a little bit about that. Network, storage, compute. Understand where your bottlenecks might be and architect to eliminate those. Try not to architect around them. Try to architect to eliminate those. I/O constraints typically are network and storage. So again, understand what those requirements are for your applications and services. And expect failure. Distributed applications and services are really made up of a bunch of discrete services, discrete code, and a lot of moving parts, as it says here. Each of those are prone to fail in their own way. So understanding potential failure points and being able to handle that failure. And so this is one of the things that, moving from enterprise where it was nothing can fail to the cloud where it's really expect failure and embrace it, architect around it, architect to handle it. And your applications and services will continue to run, continue to perform even in the event of failure. So a couple of quick architectures. This is an API web architecture that's very common with our customers. And this really is meant to illustrate that from a load balancer perspective, the API tier, the cache tier, those all tend to be virtualized server instances, so public cloud. Scale out very rapidly. And leveraging bare metal for the database. Interconnects between these, typically within a data center, very fast, low latency. So that once that request hits a load balancer to get served all the way down to the database and back up, can be very fast. But understand each tier, understand the performance implications of each tier, understand how they need to talk to each other to optimize performance at each of these. Consider each tier a discrete service. Optimize that, then optimize the interconnectivity between them. And then gaming, another big one for us. Leverages a lot of the core concepts of the API tier. Gaming a lot of times has state. So that state can be leveraged with a virtual tier. A processing on the back end can be leveraged with virtual, where they're doing number crunching. They're doing that they're applying their algorithms to the data, trying to learn more about you and mine that. And then leveraging bare metal for database and big data. One thing I want to touch on real quick is we talked a lot about virtualization. We talked about bare metal. And I say the future is now. One of the hottest things going right now is Linux containers. And this really ties into performance. And it's really a new way to do virtualization. It doesn't leverage a hypervisor. It's actually built into the kernel. And it is much more lightweight. You can actually containerize an operating system and put stuff in it. Or you can actually containerize individual applications or services. So it becomes very light. It just ends up being that application, that service, and its dependencies. It's in the kernel, so it's very fast. And LXC is actually a technology built into the kernel, built into the operating system, and in and of itself is not a set of tools. If you compare it to the hypervisors, whereas hypervisors really isolate and build up an entire operating system within a virtual machine and carve up resources across that, Linux containers actually run on top of the operating system. And they end up being processes running within the operating system. So they become very fast to create, very fast to destroy if you need to, and much easier to deploy across multiple servers because of the container nature of it, encapsulation. And Docker is the one that made this take off. So this week is DockerCon. Docker just released 1.0. Docker is an open platform that allows developers and sysadmins to really develop, deploy distributed applications. And they can be very discrete. There was an IBM presentation at DockerCon by Jerry Cuomo and Andrew Spiker. And that's a link to kind of a summary of that. But Docker right now is probably the hottest thing going in technology. If you haven't heard about Docker, you haven't looked at Docker, I would suggest take a look at it. The performance implications are still coming. Right now, it's really focused around that ability to easily containerize or package and be able to move that from your laptop to your dev server to your test server to production without having to really do anything to that core set of code. It's just going to run in any of those environments. That's kind of the promise of it right now, and it's delivered upon. But as it starts making its way into production systems, the performance implications are really substantial in terms of rapid provisioning and then the overall performance of it, because it's being able to take advantage of the core kernel. So quick summary. Cloud adoption obviously continues to improve. Key verticals, driving and innovating with it within the cloud. considerations, there's many factors to take into account when you go to the cloud. The biggest one for me, know your applications, know your services, and then how to best apply those to cloud architectures. Cloud architectures, really cloud providers, we at SoftLayer, we provide you the core building blocks. Leverage that for your applications. And the future is now. Cloud's evolving, not only just core cloud with bare metal and virtualized infrastructures, but new technologies like Linux containers. A couple sessions tomorrow. I'd highly recommend Bowden Russell is doing 2 talks back-to-back about Linux containers. He spoke at OpenStack. It's a great discussion. And then Harold Hannon from SoftLayer is talking about big data in a bare metal cloud. And that's it. Thank you.